So we are going to see chapter solutions. So in this chapter, we are going to see the characters of the solution, the behaviors of the solution, and then how it is involved in chemical reactions. Everything we are going to see right now. So here, what is a solution? First of all, okay, a solution, it comprises a solute and the solvent. Okay, so what is a solution? A solute and solvent. Okay, so when we can say a solution is a homogeneous mixture. So there are two types of mixtures you have studied. So this is homogeneous mixtures, okay, of two or more compounds or two or more substances when it is connected. So it is homogeneous. And then you know about the solvent and the solutes. So a solvent should be always a component of larger quantity, and solute should be the components present in a very desirable amount. For example, if you are preparing sugar solution, always I'm insisting all the children to connect the chemistry with the kitchen things. We are talking about the sugar solution. Everyone knew. So if you are adding 1 liter of water, in 1 liter of water, 1 kilo of sugar, then you will not be getting a proper solution, right? So if you add in 1 liter of water, so if you add 100 grams of sugar, then it will go off in a proper solution. So it will be spontaneously, without any heat, it is dissolved, completely dissolved in the water. So this is said to be solvent, which is in larger amount, larger concentration, or we may say this component, water is the larger component or a larger quantity. And then this sugar will be desirable. Okay, solutions we are going to learn. Okay, solid solutions, liquid solutions, and gaseous solutions. And then you know what is gaseous solutions, gas, liquid, solid. That is the solute. The solute might be anything. So what is meant by homogeneous mixtures? Here comes the point. Mixtures of two or more, components or elements, right? So in that, the solvent should be of the same phase, so that homogeneous. What is the homogeneous actually? If you are going to produce gaseous solutions, then that should be homogeneous. So in gaseous solutions, all solvent should be gas. So the larger component should be in a gas phase, okay, gas state. So the solute might be anything, gas, liquid, or solid. So you can have this common examples, oxygen and nitrogen. So gas and gas. So the example is you can mix up oxygen and nitrogen and then it produce nitrogen dioxide, right? So that we know that is the solution basically. So then chloroform is mixed with nitrogen gas. So liquid with gas. Then camphor, everybody knew, with nitrogen gas. So nitrogen gas plays a vital role in producing solution, right? So solute and solvent is defined over here. So likewise, liquid and liquid solutions. So all solvent might be any form of state, but solute might be any form of state, but the solvent should be of the same state, that is liquid state for liquid solutions. Got it? So then, what is solid solutions? So it should contain the solvent in a same state and remaining solute as a different states. Okay, any states might be there, any 3 states. So many examples are given. You should keep in your mind all these examples. Okay, so we can express all these kinds of composition of solution in terms of these quantities. For example, molarity, mole fractions, then percentages, molality. So you must know the difference between all these quantities. This is very important. So you can refer this video for your knowledge, and then I'll explain you about the important concepts which is involved in questions. Okay, so carefully watch it. It's very important. Composition of solution can be described by expressing its concentration. Very, very important. So concentration is very important. So first we are going to see about mass percentage. What is the mass percentage? Mass of the component in the solution by total mass of the solution. What is this component actually? The component means in the solution we might have seen two or more components, two or more substances, right? Elements. So out of it, what component you are choosing up? What is the component? For example, C3 H7. For example, if you are taking C6H12O6 in glucose, okay, in this fructose sugar, if you want to find the carbon's concentration, so carbon is one of the component, hydrogen is one of the component, oxygen is one of the component. If you want to find the carbon's concentration, then you must come across this component, the mass of this component in the particular solution, and then total mass of the solution. So you have to add all the total mass of the solution into 100. Since it is percentage, so you have to include 100%. So example is given. So 10% of glucose in water. Okay. So if you want to find, so glucose individually, glucose plus water. Okay, so 90 gram of water and then 10 gram of glucose. So total mass will be 100 grams. Okay, and then what is the glucose actually percentage will be 10%, right? So out of it, you have to find. So 10 gram by 100. Okay, into 100. So 10%. It is described like this. Okay, so it is commonly used in industrial chemical applications. Suppose in pharmaceutical companies and then in food industries, then suppose they are adding some preservatives to the food industries in order to preserve the food. Okay, packed items, everything. They'll definitely stick on to the ratios. They'll definitely stick on to this mass percentage. This is very important for them. So in a particular solution, the mass percentage should be calculated by means of this formula. You just keep in your mind. Mass percentage is equal to mass of the component in the solution divided by the total mass of the solution into 100. So what is the volume percentage? The volume percentage might be volume of the component by total volume into 100. Same. So you are given for each and everything, some examples I've discussed over here. So many examples you might have come across in Google. You just Google it and you can add on, include so many examples in this. Okay, so you can type like this: examples for mass percentage, examples for volume percentage. Okay, so you'll get so many examples. You just have a look of that. Keep in your mind all the examples. You must come across volume percentage, mass percentage, both the thing. So what is mass by volume percentage? So mass by volume will be W by V. Okay, so this is another unit which is commonly used in medicine and pharmacy. It is mass by volume percentage. Okay, so it is the mass of solute dissolved in 100 ml of the solution. That's it. Okay, mass of the solute in grams by volume in ml. That's it. Then parts per million. So when a solute is present in trace quantities, for example, we are adding a little pinch of salt for a bowl of soup, right? So like that. So this is such a trace quantities. Suppose if you want to know about any adulterants in that, the adulterants might not be in a bigger quantity. It is also in the trace quantities. It is convenient to express concentration in parts per million. So this is parts per million. So for million thingy, it is 1 part like that. So number of parts of the component divided by total number of parts of all components of the solution. This is very important. You are stick on to one component in the numerator. That is number of parts of the component. divided by the total number of parts of all components of the solution. For making sambar, you will add so many ingredients. Okay. So in that, salt is one of the component. So you are talking about that part, number of parts of that component divided by total number of parts of all components of the solution into 10 raised to 6. So what is this 10 power 6? 10 power 6 is million. So don't forget to multiply this 10 power 6. This is very important in this case. So concentration in parts per million can also be expressed as mass to mass. So that also we can express instead of number, we can express in mass. So then volume to volume also we can express, and mass to volume also we can express. So for example, a little of seawater which weighs 1030 gram contain 6 into 10 raised to minus 3 gram of dissolved oxygen. Okay, so if you want to find the dissolved oxygen in that particular seawater, then it will gives you 1030 gram, right? Such a small concentration is also expressed as 5.8 gram per 10 power 6. Okay, so this 10 power 6 is very important. That is parts per million, okay, of seawater. This is an example. Likewise, I've always mentioning you, just Google it, all examples, extra examples. Okay, so mole fraction, this commonly used symbol for mole fraction is X. Okay, so keep in your mind this lesson. The students, those who are very new to this class 12 chemistry, you must be aware of the symbols. This is very important. So this is the symbol, and then mole fraction of the component can be represented by number of moles of the component divided by total number of moles of all the components. Okay, so for example, if you are taking number of moles of A and B, okay, that A be solute and then B be the solvent, like that. Okay, so this A be the solute, we can take it like that. Then B be the solvent. Then what is the number of mole fraction of a component? So mole fraction of a component A, we are talking about which component now? A, that might be solute. If you want to find the mole fraction of a component A, then that should be number of moles of the component Na divided by total number of moles of all the components. So Na plus Nb. Suppose if you are having more than 2 number of components, then you have to add like this. So until ith component, okay. So n1 plus n2 plus etc. until ith component, and then you are talking about the first component. Suppose if you are taking the mole fraction of a second component, you should write n2 by summation over all ni's. Like that you can include. So this mole fraction also be related to so many components, right? This numerator also be varying to so many components. So like this x1, we can calculate x2. x2 is, as I told you now, n2 by n1 plus n2 plus n3 etc. until ni, or summation over ni. What is x3? x3 will be n3 by summation over ni. Likewise, you can have all kinds of mole fractions, all mole fractions of different components which is used in the solution. So when you add all these mole fractions, then that leads to 1. You know that, right? What is this? Ni, right? So if you are adding all these things until Ni, okay? So plus etc. until Ni. So in the numerator also you'll be having etc. until Ni. The denominator also etc. Ni. Okay. So these two gets cancelled, then the resultant will be 1. So mole fraction unit is very useful in relating some physical properties of solution. Say vapor pressure with the concentration of the solution. We can relate vapor pressure with the concentration of the solution, and quite useful in describing the calculations involving gas mixtures also. So this example is very important. So ethylene glycol is okay. So the mole, you are asked to find the mole fraction of ethylene glycol in a solution containing 20% of C2H6O2 by mass. Okay, so here it is given by mass. As we have discussed, all mole fractions or any components can be expressed in mass to mass or volume to volume or mass to volume, whatever it might be. So assume that we have 100 gram of solution. Okay. So because 20% is given, you can assume it like that. So by mass, so suppose if you want to assume like 1000 gram, you can assume like that. But we are usually taking mass by 100 gram. Then we can assume volume as 1000 liter. So 1 liter like that. 1000 ml. Okay. So likewise, we can get it. So volume is 1 liter or 1000 ml. So this will be 100 grams. Mass will be 100 grams. So what it is, molar mass of C2H6O2 we have to find. So what is C2H6O2? Carbon has 6 atomic number is 6. So number of moles is 2. So 6 into 2. So the hydrogen's atomic number is 1. So the number of moles is 6. So then oxygen 16 into 2. Okay, so we can take all these things because oxygen is always diatomic. So 12 plus 6 plus 32, that will be 62 gram per mole. This is the molar mass of the given ethylene glycol. Then moles of ethylene glycol is 20% they give. So out of 100 gram, 20% will be 20 gram. So 20 gram divided by the molar mass. So that will be the moles of that particular ethylene glycol. Then it should be added up with the water. So what is the moles of water? Remaining 80, right? Out of 100, 20 grams is, ethylene glycol, then the remaining will be water. So by what is the water, molar mass of water you have to find? 2 into 1 plus 16, that is equal to 18. So 18 gram, that will be this. This is the moles of water. So this is the mole fraction of glycol. That is the ethylene glycol. What is the mole fraction of ethylene glycol? Moles of ethylene glycol divided by the moles of ethylene glycol plus moles of water. So this is the formula we have learned here, right? This is the mole fraction. So this will gives you 0.068. Students, keep in your mind this numerical calculations are very important. When you calculate 0.322, then 0.322 plus 4.444, then first you have to add this thing. So 4.766, so 0.322. Since these two have 3 decimal, okay, so you can avoid this 3 decimal because if you remove this decimal, so 322 should be divided by 1000. Then if you remove this decimal, then this is also divided by 1000. So you can take 322 as a dividend and 4766 as the divisor. Okay, then put on point. Okay, 0. Then it is not enough, right? This is near about. So in this kind of division, you can round up in your mind. Okay, and then do properly appropriate value in this calculation. So you can think it of in an average in your mind. So 4766, you can take it as 5000. 3222, you can take it as 3000 like that. So it will not go. So put again 0. So it will be 32,000 and then 5,000. So you can think it out. So in 32,000, 5,000 will be 5 times. 6 5s are 30, sorry. 6 5s are 30, right? So you can multiply. Likewise, in your mind, you can think in an average. You can round off and then think. While doing calculation, you should be, in a pakka manner. So each and everything should be in appropriate. So 6 times of 6 is 36. So 39. So 45. Then so 24 plus 5, 29. So reminder, so 4, 0, 7, then 2, right. So then you can add again 2 zeros, okay. So 0.06, then you keep it as 5. So how many times it will be like that? It will be continuing, okay. So likewise, you should do the calculations. Keep in your mind, this is very, very important. So keep everything in your mind. like this. Okay, so this is example 2.1. If you want to find the mole fraction of water, then you have to do with the water. Okay, number of moles of water. Okay, so mole fraction of water can also be expressed in this time or in this method also. You know that only water and then glucose is added. Then glycol is added. So glycol, then water. Right. So glycol and water, the mole fraction, if you add both glycol and water, the mole fraction will be equal to 1. Suppose if you find one thing, you can calculate the other by subtracting from 1. So this is one method. Then we are going to talk about molarity. See, this molarity will be moles of solute by volume of solution in liter. Moles of solute. Only you're taking solute as molarity. Okay. With respect to volume of solution in liter. So that also given one example. You just go through it. It's very direct example. You can use the formula and then substitute. That's it. Molality will be mass of moles of solute by mass of solvent. Here, moles of solute by volume of solution. In molarity, for molality, mass of solute by mass of solvent in kilogram. Don't confuse with these two things. Okay. So that also you are given example and then problem. You just have a look of this, and then this in-text questions and all. So these are also very helpful. Let me do this in-text questions. So what it is represents. So first of all, you are given okay. What is the first question? Calculate the mass percentage of benzene and carbon tetrachloride. Okay. So both are given molecular formula. Then if 22 gram of benzene is dissolved in 120 gram of carbon tetrachloride, it's given like that. Let us move on to that. So what is the question? The question here is mass percentage you're asked. Okay. So calculate the mass percentage of benzene. Benzene molecular formula is given like C6H6 and then carbon tetrachloride. Okay, CCl4. Okay. So 22 gram of benzene, C6H6 and 122 gram of carbon tetrachloride, CCl4. Okay, you're asked to find the mass percentage. What is the formula for mass percentage? Mass of the component, let this be X, we can take, okay, mass of X by mass of total mixture. Total mixture into 100, right? That, so don't forget to put this 100 here. So mass of the total mixture we are going to find. What is mass of total mixture? Mixture will be 22 plus 122. That is equal to 144 grams. Okay. So mass percentage of benzene we are going to find is equal to 22 by 144. That's it. This is the formula. Into 100. Calculate this. Okay. And then mass percentage of CCl4. That is equal to 122 by 144 into 100. So what is this? 11. Then what is this? 60. Okay. 72. Right. 11 and 11 divided by 72. So 1100 divided by 72. Okay. So take down in this. So it will be 172, remainder 8, 3. So 380.